an electric field of 0. That's what we're looking at here. Okay? So electric shielding is our last big idea for this unit. And it's a very simple idea. Inside a metal conducting shell, there can be no electric field. Okay? Why? Well, first of all, quick review, right? What's an electric field? It's a space that surrounds a charge, and it's a force field. Okay? If you have a source of charge, like if I turn off my cool little plasma globe, these things are so fun. Anyone have one of these at home? They used to be like really expensive, and now I think you get them for like 20 bucks on sale at the mall. But anyhow, no source of charge, no electric field, right? So once you have a source of charge, all of modern life is made possible because we can store energy inside this force field of electric charges, and we can move charges from one place to another, okay? So anyway, if you have a metal conducting shell, the field inside has to be 0, okay? That's kind of weird. Why? There's a couple ways you can think of it, but we're going to try to simplify the reason why there. And the basic idea is, let's say we had a bunch of electrons inside this piece of metal here, okay? Basic rule of electrostatics. Do electrons like electrons? Opposites attract, right? But like charges will repel there, right? So if you have a metal shell, and if I had electrons in there, they don't like each other, right? They want their own space there. So like when the seniors, you guys take off to college and you get your own dorm room, a lot of you guys will have a roommate. Maybe you'll be stuck in like a triple or a quad. You'll have 3 or 4 people there. And let's say suddenly they open up extra rooms because they got extra space on your dorm floor, right? So you're going to stay stuck in a room with like 4 other guys who maybe shower when they're supposed to, or do you want to take your own room? Probably you're going to like run away, right? So eventually any net charge on the inside of a metal conducting shell will all go to the outside and spread out as far as possible, like our Van de Graaff generator, right? So eventually they'll distribute on the surface and it'll hit this state called equilibrium. Notice the word in the root of equilibrium. What's that root there? Equal, right? Or equi or whatever, right? If you're taking Latin or that etymology class, something like that, right? Okay? So basically, since charges don't like each other, they're going to all hide on the outside there. And if you don't have a source of charge, then you can't have a field there. It's the idea. Simple idea. Okay? Another way to look at that is if you think of it as the force vectors pushing the charges around. If you have a parallel component along the surface, it'll move charges along till they hit equilibrium. And then they'll end up flowing perpendicular to the final surface. So in real life, we see shielding happen naturally and also unnaturally. So one dramatic example is actually airplanes. So every year, most commercial jetliners are struck anywhere from like 3 to 4 times. But you don't really hear about it on the news too much because most airplanes are made out of what? Woo! Out of metal, right? Like aircraft aluminum. So the metal shell of the plane protects it from the lightning strikes because an airplane is basically like a natural lightning rod as it flies to a thundercloud. The lightning then will conduct around the outside of that metal shell. So as long as it doesn't burn through, this is a really cool picture here, scanned in out of an old National Geographic feature issue here, where the blast panel on the left, the lightning strike didn't burn through here. But the one on the right-hand side, the lightning actually burnt through and started a fire. And then that's not good, okay? So one big problem now is we're starting to make airplanes out of composite materials, like carbon fiber. So like the new Boeing Dreamliner, I don't know if you guys heard about that in the news, finally rolling off production line and all that. It's really lightweight because it's made out of carbon fiber, and the wings are super flexible. I think it almost bends like 45 degrees up. So it's really strong, really lightweight, fuel efficient. But the problem is if there's a lightning strike, then you don't get that shielding effect. So you have to make sure to shield the sensitive electronics there, okay? The other practical application where you can see this, besides the impractical one, which we're going to do in a second, is in cables. So you know when you're hooking up your home theater system, your HD TV and all that, most cables have what on the outside if you want to make a cable at home? Common sense, right? You should use like a rubber or plastic material, which is a good what? Insulator, right? And then you have copper or steel on the inside as a good conductor. But a lot of cables, they have multiple layers, right? So why would you do that? It's because you want to shield it, is the idea. So if the cable guy comes out and is hooking up your Comcast, Triple Play, Uverse, whatever, right? You don't want signals leaking out and messing up your stereo, your TV, and all that. Or those of you, when you go off to college, you might get a docking station for your laptop. Well, then you want to make sure if you have speakers, you know, so you got your iTunes grooving and all that, that the speakers are shielded so that the signals don't mess up your screen there, okay? So shielding is a natural idea and also a technological one. We can apply it. So in the old U.S. Embassy in the former Soviet Union, they actually had a Faraday room, a big metal room there, right? So why would you want to do that if you had an embassy in the former Soviet Union and were worried about secrets during the Cold War? So that, I'm sorry? Oh, okay, that's okay. Yeah, it's so you can keep your secrets secret, right? So the KGB can't try to spy on you, try to pick up signals and all that. But the converse is true too. No signals will get out there, okay? So to demonstrate shielding, we're going to do 2 crazy examples. First one is actually need a volunteer to turn on their cell phone and turn on your ringer as loud as possible. And if you have a really obnoxious ringtone, even better, okay? So normally you get in trouble in other classes, but now I actually want you to do that on purpose. So I need a volunteer to go ahead and turn on their cell phone, crank up their volume all the way on the ringer, okay? So anyone know how a cell phone, like basic operation, how's it work? When you place a call, right, a signal sent from what? Satellite. Well, maybe satellite if you're really fancy, but usually just a cell tower, right? So just right outside the school, we got a water tower, and this district just got a contract, so we get a little revenue. Uh-oh, battery's getting low. Let's place a quick call for Ryan here. So right now, we're calling you. The phone is sending a signal to the cell tower. There we go. And we know we got the call when the cell signal gets through there, right? There we go. There we go. Oh, that's a good one. I like it. That is really annoying. That's good, Ryan. I like it. You should keep it. There we go. There we go. Perfect. There we go. Cool. Fun. Actually, yeah, you got a strong signal there, right? There we go. Awesome. Oh, let's leave Ryan a message. There we go. I only leave one. Okay. There you go.
At the tone, please record your message. When you finish recording, you may hang up or press 1 for more options. To leave a callback number, press 5.
Hey Ryan, it's Mr. Lau. Good luck studying for your physics test Friday. Make sure you do the review guide and the concept check. There we go. Thank you. Okay, just kidding. Anyhow, now, okay? What do you think? Okay? His phone's wrapped in foil. And what do you know about the electric field inside a conductor? It's got to be a what? Big fat 0. You know what? You know how we did those crazy computer simulations? Okay? I like this one to kind of show what's going on. So if I turn on the flat view, oh, here we go. And we'll do the no lines. There we go. So on the flat view, let me get the field lines flowing here. There we go. And if I flatten this here, there we go. You can see that the charges flow along the field lines and then around that conducting shell there. Okay? So that's kind of a way to try to visualize what's going on once we wrap this phone in foil here. Okay? So let me call you again. And how can we have conclusive proof then that your phone is indeed shielded? What's going to be the difference now? Yeah, okay, we shouldn't get a signal here. So one common misconception is that when you're inside a building, you know when you drive under a bridge and your radio cuts out, that everyone thinks that it's the concrete that's cutting the signal out. Not at all, right? So what's inside concrete? Anyone know? Bunch of, oh, is that just your batteries low? Oh, okay. There we go. There's a bunch of metal rebar is what it's called. So it acts as a Faraday cage, a shield. Yeah, there we go, right? And you know what, Ryan? I won't leave you another message. That'd be really annoying there, okay? So, there we go. No problem. In terms of electronics, we want to take advantage of that idea to shield excess signals there, okay? So if you have a friend who's really annoying, like, you know, you go to the movies and their phone's always going off and they're texting, or you're having lunch and like, hello, social skills, I'm here, you know, so, right? Just wrap their phone in foil, and that'll throw them off there, okay, for April Fool's prank. They'll probably be like, what's with the Chipotle, right? Like, I don't get it. So, you know, another cool practical example is, you know the iPass system that we have, the little iPass receivers? I had to get one for my wife's other car 1 year there, and when I got it in the mail, it actually came wrapped in foil. And I'm like, that's kind of weird. Actually, it'd be cool if you got a free burrito, right, at Chipotle there. So, like, what's going on? So, if you think about it, it actually makes sense. Why would they mail you an iPass transponder wrapped in foil? So that way, when the UPS guys deliver it, right, you're not getting charged every time they drive through. So it's actually pretty smart. Looks like maybe the state of Illinois, they know a little bit about what they're doing there. Okay? Next, we're going to do the classic Faraday cage demonstration there. Now, I do have to give credit where credit's due. This demonstration came not from me, but from a student who didn't believe when I was talking about hiding inside something metal. So 1 year, I'm like, yeah, extra credit. Bring in a dog cage, and we'll zap you there. And I didn't think the guy would do it, and he brought in a big old dog cage there, okay? So I need a volunteer who has a high tolerance to electrical pain, is not prone to seizures, doesn't wear a pacemaker, and doesn't mind tight spaces. Let's do it.